And hopefully, as this program goes on and lecture series continues, we will have greater participation from all parts of the world. I could not admit people from South America last time, but then all of those problems are taken care of from this lecture onwards. With that, let me ask Amogha to introduce Professor Tatsuya Tsukuda.
Good morning, good afternoon, and good evening to one and all present here. I welcome you all to the second lecture of our Center of Excellence lecture series on molecular materials and functions. Today's speaker is Professor Tatsuya Tsukuda, a renowned scientist in the field of atomically precise nanoclusters and their applications in catalysis. Professor Tsukuda completed his PhD in 1994 at the University of Tokyo under the supervision of Professor Tamotsu Kondo. He did his postdoctoral research in Riken, Japan. He was appointed in the Institute for Molecular Science in Okazaki as an assistant professor in 1994 and was later promoted to associate professor in 2000. Later on, Professor Tsukuda joined as a professor in Catalysis Research Center, Hokkaido University, and is currently working as a professor in Department of Chemistry, Graduate School of Science, the University of Tokyo, Japan. His research interests are mainly atomically precise synthesis and characterization of ligand-protected gold nanoclusters and their applications in catalysis. He has over 230 publications with more than 17,000 citations with an H-index of 60. He has also received many awards like CSJ Award for Creative Work from the Chemical Society of Japan in 2009. In 2019, he was admitted as a fellow of the Royal Society of Chemistry. He is the senior editor of Journal of Physical Chemistry Letters, a journal of ACS. Sir, we are all very excited to listen to your lecture. Let's give a warm welcome to Professor Tatsuya Tsukuda.
Thank you very much for the kind introduction. Okay, let me share the slide. So can you see the slide?
Yes, we can.
Okay, thank you. Okay, thank you very much. My name is Tatsuya Tsukuda from Tokyo University. I'm very happy to give a talk at this series of lecture. Today, I'm going to talk about chemically modified gold and silver clusters as an artificial element at the nanoscale. And before starting my talk, let me thank my coworkers. I have 3 professors in the group, Professor Koyasu, Professor Takano, Professor Masuda. They are the key players of this project. And Professor Koyasu is working in the gas phase measurement. And Professor Takano is the key person for the atomically precise synthesis of ligand-protected metal clusters. And Professor Masuda is an expert in the catalytic application of metal clusters. And I have nearly 20 students. So I want to thank all of them for their contribution. And before starting my talk, let me start my talk by showing some pictures with Professor Pradeep. I think I met him nearly 15 years ago when I was in IMS. Since then, we have been working together in the same field. And I have enjoyed very much working with him. I was so lucky to be in the same community. And I want to thank for his great contribution in many aspects in our community. Okay, so here's a motivation and the target of our research. We are interested in very small metal clusters with a diameter of 1 nanometer or so. And as Professor Pradeep already told you in the previous lecture, these smaller clusters can be built as molecules rather than metal because of quantization of the electronic structures like this. And also clusters are unique in terms of geometrical structures. As you know, in the case of gold, gold takes FCC packing, and our particles also takes FCC. But when we go to the cluster regime, the clusters tend to form 5-hole symmetrical structures like icosahedron. So atomic structures and electronic structures are very different from corresponding nanoparticles. So we can expect some unusual, interesting properties emerge in the cluster regime. So we are working on different types of clusters, like clusters protected by organic ligands, clusters weakly stabilized by polymers, and the clusters immobilized on the solid materials. And especially these two are for the catalytic application, and this one is for fundamental interest about the structure property correlation. So we have been developing an atomically precise synthesis of these type of metal clusters, and we are interested in understanding of the correlation between structures and properties. And our main target is gold clusters. This is because we have already a lot of lessons from the studies of the naked gold clusters in vacuum. Here I list up several key professors, Professor Kapes, Weten, Akinen. They are on the list of the speakers, and they are the key players in this field. And in the case of gold clusters, naked gold clusters in vacuum, we know these clusters are magic clusters, okay, 20, 34, 58. And the high stability of these magic clusters have been explained by the closure of the electric shell. So the 6 s electrons in gold atoms are accommodated into discrete orbitals created within the Jerem-like potential of the clusters. So when the total number of electrons satisfy these numbers to 8, 18, 20, and so on, the clusters become stabilized because of the closure of the electronic shell. So electronic structure is very important when you talk about the stability of gold clusters. So this is the lesson we have from the gas phase studies. And also chemical reactivity can be also explained by the electric structures. For example, the reactivity against oxygen molecules can be explained by the electric shell. So from these studies, we understand we must control the cluster size with atomic precision. Otherwise, we cannot say anything about the structure property correlation. So this is the mission we have to achieve. Okay, atomically precise synthesis is necessary. And in order to stabilize the clusters against aggregation, we need ligands, okay, to prohibit the contact, okay. So as a ligand, thiol has been used as a promising ligand since the first report by Professor Brust and Schifrin in 1994, because the gold sulfur has a strong affinity. And soon after the first report of the synthesis of gold nanoparticles protected by thiol, Professor Weten discovered that there are a series of magic species, magic clusters in thiol-protected gold clusters. And here is the mass spec of the isolated gold thiolate clusters. So we know there is a series of magic species by this important work. And also Professor Wetten and Murray reported the molecular-like charging of a small thyroid protected clusters. So this is the evidence that the clusters have molecular-like electronic structures. So inspired by these stimulating works, we try to establish the atomically precise synthesis of ligand or thyroid protected gold clusters. So I show you our method to achieve this synthesis. The first step is the preparation of the mixture of magic clusters by chemical reduction in solution. So the left one, it's not working. So here's the movie after putting reducing agent into the gold 3 ions. So you can see black powders. So we have basically bulk gold in solution without any protecting reagent. But when we reduce gold sulfur complex, in this case, gold is formally 1+, and after addition of sodium borohydride, the reduction takes place very rapidly, and you can see transparent brownish color. So this is the mixture of the stable magic clusters in solution. And after adding excess amount of thiol in this solution, some metastable species are etched into small stable species. So size focusing occurs in solution. So just after this process, we have a mixture of magic clusters in solution. So then the next step should be the fractionation of the clusters by some way. So step 2 is the fractionation. So we employ gel electrophoresis and chromatographic method to separate the clusters by size. And after size separation, we have a series of clusters with different colors like this, starting from this brownish mixture. Okay, then final step is the determination of the molecular formula by mass spectrometry. So we employ ESI, electrospray ionization, which is known as the soft ionization method. And the Professor Pradeep and the Professor Jampin-Sheh also use this method to characterize the clusters. So this is the first demonstration of the gold 2518 clusters, which is well known as a very stable species nowadays. So by using this method, we can synthesize atomically precise clusters in cities. Okay, then after the synthesis, our community has achieved a deep understanding of the structures. So as for the geometrical structures, Professor Kornberg reported very important results. And before this paper, we thought that the core is directly protected by thiol, but this was not the case. For example, in case of 102 thiolate 44, the core is made of 79 electrons, 79 atoms, and the total number of electrons confined in the core is 58. And this 58 is also the very good numbers, as you can see here. So electronically closed core is formed, and the surface is protected by the combination of gold sulfur oligomers with different lengths and with a staple motif. Okay, so this is the common structure motif, metallic core, and the surface is covered by these type of oligomers. Okay, what about the electronic structures? And as I told you, the naked clusters, stability of naked clusters are determined by electric shell. So the a similar picture can be applied for the ligand protected system. And the Professor Hakkinen proposed a very simple electron counting method, okay, confined in the core. And according to this simple method, we can calculate the number of electrons confined in the core of 25 thiol 80 minus is 8. Okay, so we can expect that 8 electrons are accommodated into 1s-like orbitals and the 3 degenerate 1p orbitals like this. And actually, according to DFT calculations, the shape of the orbitals which confine the electrons looks like atomic orbitals like this. Here it looks like s orbital. It looks like p orbitals. So superatomic picture can be applied to understand the structures of ligand or thyroid protected gold clusters. So chemically modified or ligand protected clusters can be viewed as superatoms, chemically modified superatoms. Okay. And the unique feature of chemically modified superatoms is that they have a variety of structure parameters like size of the core and chemical composition of the core. And we can also change the shape of the metallic core. And we can also choose the chemical species on the surface. Here is the gold thyroid system, and we can use alkenyl, and we can use phosphine, and we can use carbene. So we have a lot of choice for chemical modification. So chemically modified superatoms have a variety of parameters which determine the properties of the whole system. So I would like to show you some examples of the correlation between these structure parameters, namely the size, composition, shape, and surface modification. And lastly, I would like to tell you about our recent work on the development of new synthetic methods of superatom-based materials. So let me start with the size effect. So as I told you, we can synthesize a series of clusters by the method. And here is the mass spec of the dodecan thiol protected gold clusters, starting from 38 up to nearly 520. And here is the mass spec. And you can see the clusters are atomically precise. And we measure the optical absorption spectra of these clusters, and you can see here that the localized surface plasmon resonance at the 520 nanometer disappears when we go from 187 to 144. And when we go beyond these clusters, they show discrete structures in the optical absorption spectra. This indicates that the cluster's electronic structures are quantized, as we can expect. So the metal to non-metal transition takes place at these critical size in this case. And we also see that geometric structures also change from FCC to non-FCC structures at this critical size. So here are the structures of gold core and the silver core reported so far. And when we count the number of electrons for these cores, these smaller clusters can be explained by the electric shell closure. But for these clusters, number of electrons are 81 and 84. These numbers are not good for the electron counting. So for the clusters smaller than this region, the electron counting is important. But for these clusters, larger clusters, maybe the geometrical packing is a key parameter of the stability. And in the case of silver clusters, these smaller clusters satisfy the electric shell closure. So the message is that these small clusters, the electric shell closure is important for these smaller gold and silver clusters. Okay, let me move on to the effect of composition on the properties. So I focus on the photoluminescence properties. Okay. So recently we successfully doped a single ruthenium atom at the center of the gold-13 core. And this is a single crystal structure. And these clusters exhibit intense photoluminescence with a quantum yield of 38% in the absence of oxygen. Okay. But when we introduce oxygen, this luminescence is quenched almost completely. And we also observe the formation of the singlet oxygen under the photoirradiation. So we assign this band as a phosphorescence from the triplet state of gold clusters. But when we reduce the temperature of the system, the luminescence peak is gradually shifted, and below 120 Kelvin, the peak is suddenly shifted, blue shifted. And we assign this intense band as the fluorescence from the singlet states. So depending on the temperature, the origin of the luminescence changes from phosphorescence and fluorescence. But I want to emphasize that quantum yield is very high by just adding a single atom, foreign element at the center. So the doping effects is significant in the photoluminescence property. And we expand this study, and we are now conducting systematic study. And here is an example. So we can successfully dope a single atom, iridium, platinum, palladium atom at the center of the gold-13 core. And we see intense fluorescence, luminescence. And again, the quantum yield is nearly 70% in case of iridium doping. And this is almost completely quenched by the oxygen. So this is assigned as phosphorescence. So we are now studying the photophysical properties of doped gold-13 superatoms. Okay, so let me tell you about the effect of shape on the properties. And I show you two examples of the chloride superatoms. And gold-38 Sil-24 was identified in 2028. And according to the FT calculation by Professor Aikins, we know that the core is made of 23 atoms, and it forms a bi-icosahedral core. Two icosahedrons share 3 atoms to form gold-23. So this is a theoretical prediction. And just after this prediction, Professor Oncha-Jin reported the single crystal XRD results, and it confirms the formation of bi-icosahedral core. And another type of bi-icosahedral core is found in gold-23, protected by the combination of 3 different ligands. And as you can see in this crystal structure, 2 icosahedrons are sharing a single atom to form gold-25 core. And the total number of electrons confined in the core is 14 and 16. And in this case, we can see this dimer as corresponding to rare gas dimer, because 16 is the double of 8 electron. So electron shell is closed with 8, and they weakly bound together to form this dimer. Okay, then what about this structure, 23? And this 23 can be viewed as a prolate superatoms. And according to this simple consideration, we can explain the closure of the electric shell with 14 electrons. So these superatomic orbitals are split like this in the prolate form, and the 14 electrons can close the electric shell. So this is a typical way to explain this electric structure. But another way to explain this structure is like this. So we can see this as a dimer or superatomic molecules made of 7 electron superatoms. So this dimer is corresponding to F2 with 14 electrons. And these molecular orbital-like structure is very similar to those of F2. So this is another way to interpret the prolate superatoms. And we call this as superatomic molecules. And this type of superatomic molecules can be found in other systems. And one of my students creates this type of clusters having a gold 7 at the core. Okay, and this corresponds to helium dimer. Okay. And this is another example. When we use this bulky thiol, we have these structures. And the core of this cluster is composed of a pair of trimer, gold trimer, you can see. And the electric structure of the core is corresponding to very weakly bound hydrogen atoms, okay? Because there is no actually bonding between these two atoms. And the trimer pairs are weakly bound by the this framework, supported by this framework. Okay. Okay, so this is another example of the superatomic molecules. And we can create these polymers of cubic octahedral gold 13 by a slow reduction. Okay, and the color of this cluster is greenish, and it shows very intense band in the IR region. And here's another example. And as you can see by TEM, this is not atomically precise, but as you can see by this TEM, the diameter is always smaller than 2 nanometer, but we can change the length of the structures like this. And this looks like a very tiny rod, okay? And these clusters exhibit localized surface plasmon along the longitudinal mode, okay? And this mode is redshifted with increase in the aspect ratio. And this one is very intense band. And after, by the high resolution TM analysis, we can propose that this rod shape is composed of 147 like stable unit in like this. So this corresponds to the polymer of the superatoms. Okay, so then let me move on to the surface modification effect. So the primary role of the surface is the suppression of the or prohibition of the aggregation of the metallic core. Okay, but ligand plays more role. Actually, these are the optical spectra of gold 13 and silver 13 protected by different type of ligands. And the total number of electrons are always 8 in both systems. But as you can see, the optical spectrums are very, very different. So the ligand is plays a very important role on the electronic structures. And I'll show you some examples of the importance of the ligands on the stability and the structures of gold superatoms. And this is the gold 11 clusters protected by phosphine. This is the most famous classical system. And this cluster has some reasonable stability, but when we boil the solution of clusters, it decomposes like this. But we successfully replace one of the phosphines located between two chlorides with the carbene, and this is a single crystal structure. And by this simple replacement enhances the stability of the system, and we can use these clusters as electrocatalytic system reduction of CO2. So single carbene can enhance the stability dramatically. So inspired by this discovery, we tried to synthesize gold 13 with full protection of carbene, and this is single crystal structure. And this is very, very stable, and it exhibits the photoluminescence with high quantum yield of 60%. So the carbene is another promising ligand to stabilize the system. And the ligand can induce the chirality by using chiral ligands like BINAP or diop. These are bidentate chiral ligands. And by using these ligands as a protecting reagent, we can induce the CD activity like this. And the enhancement of CD is bigger by using BINAP. So we thought that the pi electron system also contribute to the enhancement of the CD activities. Okay, so let me skip this slide. Okay, so this is another example, effect of electron transfer. So in this case, ligand is also important. As we already heard from Professor Pradeep, the clusters in solutions exchange metals and ligands. So they are rather dynamic, okay, as reported by Professor Pradeep. And we recently found that electron can be transferred spontaneously between the clusters. So this is the electron transfer we discovered. We mix the clusters with 8 electron and 6 electron. The electron transfer takes place spontaneously in solution, and we have open shell superatoms. This looks very strange, but the efficiency is very high, almost 100% yield. And now we are studying the dependence of the length of the alkynyl group. And surprisingly, the electron transfer reaction rate increases with increase in the chain length. So maybe this is the opposite to our expectation, because this layer is insulating layer. But I think we think that it is important that the lifetime of the dimer is important to for this electron transfer, and we think that the lifetime of the dimer is enhanced by the increase of the chain length due to the weak van der Waals interaction. So now we are studying the effect of chain length on the electron transfer. And okay, so the ligand or surfactant is important for when we think about the catalytic application. And this work has been inspired by the discovery by Professor Alta long time ago. And he discovered that gold in nanoscale can oxidize CO, and the gold clusters can act as a catalyst for CO oxidation. And very sadly, he passed away very recently. Okay. But anyway, we found this discovery is very interesting, and we use polymers as a stabilizer of gold clusters. And because some of the surface are exposed for chemical transformation by using polymer as a stabilizer. And we changed the diameter of the clusters, and we found that the activity for alcohol oxidation in water can enhance like this with decreasing size, the activity enhances. So the small clusters actually act as a catalyst for oxidation in water. But in those days, there are some size distribution. The cluster size are rather monodispersed, but when we talk about the atomic precision, there's a distribution in size. And recently, we successfully synthesized atomically precise clusters protected by polymer. The key device is a micromixer. We mix these two solutions, gold ions and reducing agent, by using micromixer. And this allows us to mix two solutions homogeneously. And we also optimize the gold polymer ratio. And when we increase the polymer contents, we can suppress the size like this. This is a multi-mass spec of the clusters stabilized by PVP. And under some condition, we can synthesize gold-24 selectively. And but as you can imagine, the clusters cannot be crystallized because the polymer structures are rather random. So in order to study the structures, we used high resolution TM. Okay, so this is a TM video of the single gold-24 stabilized by BP. So you can see the atoms moving. Okay, so we assign these snapshots with the help of DFT calculations. So we found 7 isomers, and we simulate the TM image looking at different directions for individual isomers. And we assigned the structures by automatic matching of the images with the snapshots of the video. And we realized that the structures are polydispersed. We cannot explain the image by the single clusters. We have to take into account of the presence of isomers. And for example, this particle can be assigned to the most stable isomer. This one is the structure and so on. So actually, the 24 clusters are the mixture of polydispersed structures. And for the single particles, the structures are always changing like this. So cluster at gold-24 is rather dynamic under the TEM observation. So this stage, we cannot explain why gold-24 is observed as a magic species, but we realize that the structures are rather fragile, flexible, and I think that the structures are always changing in solution, and they undergo catalytic conversion. And this gold-24 actually oxidizes alcohol in water by using dissolved oxygen as an oxidant. And according to Hammett and Arrhenius plot and kinetic isotope effect, we propose that the hydride elimination from alcohol is the rate determining step. So the gold-24 clusters abstract hydride from alcohol to form aldehyde. So this step is the rate determining step. And now we are now trying to synthesize other clusters, and we are now trying to dope other element into gold-24. And so this is under progress. Okay, so in the last few minutes, I want to show you some examples of the new synthetic method of superatomic based materials. So one of the challenges for the synthesis is the low yield. Yield is not usually very high. Typically we can get a few milligrams of some clusters. So this is low yield is a challenge. So in order to overcome these difficulties, we are now trying to develop transformation reactions. Okay, transformation from some clusters to another cluster with high yield or high efficiency. So this is what we are going to do. And but in order to stimulate reactions, we have to activate the clusters. So I'll show you our approach. So we use hydrogen as an activator, and according to the gas phase studies, hydrogen mimics gold. Okay, so the electric structures of gold 7 and gold 6 hydrogen is very similar. Electron affinity is very similar, and one of the gold atoms of gold 20 can be replaced with hydrogen, and the homolume gap is almost equivalent. So hydrogen mimics gold in the naked gold clusters. And this behavior is also reported, theoretically reported for the thiol protected system. So we are interested in the interaction between hydrogen and the gold. And we use these clusters as the starting materials, gold 9 with 8 phosphines. And this is the structure. And you can see 8 atoms in the circle is capped by phosphine, but the central atom is not ligated, so it is naked. So we mix this gold 9 clusters with sodium borohydride, and we observe a duct of H- or D- to this gold 9 clusters. And according to theoretical calculation, so before the H- addition, the p orbitals are split into 2 groups. So one of the p orbitals along this direction is unstable, upshifted in energy. Okay, so and then 6 electron is a good numbers, but after addition of hydride H-, the p orbital become degenerate, and total number of electron increases to 8. And interestingly, one of the p orbitals are exposed because there's no ligand along this direction. So we can expect this species might have nucleophilicity against metal organic compounds. So here is the idea. So this is the clusters we can synthesize in a large quantity. 1 gram synthesis is possible, and by after addition of H-, it becomes activated, and it undergoes a variety of nucleophilic attack to the gold and silver and copper species to form these alloy species, alloy clusters. And when we react with these species, we can replace the ligands to thiol or alkenyl in a very high yield. So these transformations are very efficient. So we are now interested in the hydride mediated transformation reactions. And this is the last example of the reaction. So as I told you, we can have a dimer of superatoms, and these clusters are obtained accidentally. We didn't intend to make these kind of dimers. So this means that we have no hope to get hetero superatomic molecules. So in order to expand the libraries of the superatomic molecules, we study the reaction between hydride doped clusters with thiolate protected clusters. So here the palladium is at the center, and here platinum is at the center. And by mixing these 2 clusters, and we get this dimer species, heterodimer species with high yield. So this suggests that we can create hetero dimer intentionally by using the cluster fusion reactions initiated by hydride doping. So, okay, this is the last slide. And so now I'm interested in constructing a kind of periodic table, okay, using gold as an element. So we are trying to increase the number of electrons like this. And as I told you, the unique feature of a superatom, chemically modified superatom, is that they have a variety of parameters. So even though the system is 8 electron, we can tune or adjust the properties of the superatoms by controlling these parameters. And after that, once we get a variety of superatoms, maybe we can synthesize quasi molecules made by superatoms, and we can enjoy chemistry which is parallel to the conventional chemistry. So we can make this kind of assemblies in the future. Thank you very much for your kind attention, and I'm happy to answer your questions, especially from young people. Thank you very much.
Thank you, Professor Tsukuda. What a wonderful lecture. And at a, well, rather late for you, at 10, well, it is going to be 11 for you, right? It's
yes,
going to be 11 for you. So we should not keep you holding. Although you said students, young people to ask questions, and I am asking all the young people to be ready with questions, but that doesn't stop us old people from asking questions as well. So I will just start with one question, and then probably my colleagues could start asking questions, as well as students. Please be prepared to ask questions. Professor Tsukuda will be well happy to stay, although it is late, for some more time. Okay, the first question that I would like to ask is that it's great to see these electron transfer, and that throws a lot of possibilities. One immediate thought that I would like to see is that gold chemistry is similar to hydrogen, and you mentioned about that.
Yes.
How about when we know that hydride is abstracting and all that you talked about? Hydride transfer is certainly a possibility between systems, and now we know several hydride clusters. So is it possible that hydrides can also transfer not from, let us say, between gold and gold, but also gold and copper? So all of these result in a number of catalytic possibilities. So this is the first thought in that direction. I would like to hear your response. And then there is another question there. That is, why between, well, only 2 minus and 0? How about other charge possibilities? What do we know about 3 minus and something else? And neutrals and all that. So thank you. That's all.
Okay. You asked about the possibility of hydride transfer from some cluster to another cluster. I have never thought about that, but it may be possible between these maybe clusters. So this is a pure gold 9, and we can replace central gold with the palladium like this. So maybe between these two clusters, maybe hydride can be transferred, and we can detect the transfer of hydride by using mass spec. But other system, I have no clear answer for your question. maybe possible, but maybe difficult to probe. And, so maybe this does not answer your question, but it's a very difficult question.
Other charge states, what is your current thought?
Yes, I didn't study so much about that. And the key point of this system, the transfer, is that the 2- is very unstable because of charging energy. So 2- wants to release electron to 0 valence. So I think 3- is more reactive for the electron transfer. So so far we haven't studied that, but yes, it is possible to use 3- as an electron donor to the cluster.
Great, great to hear that, and 2- and the electron transfer dynamics and all that. I hope we will soon hear about all of these possibilities. Colleagues, floor is open.
So hi, this is Sundar Gopal. It's a very nice talk, interesting chemistry. Recently, I was going through one of Mingo's structure and bonding review, and I saw a lot of Pradeep's and yours molecules been listed there. It's very nice to see them all in electron counts and all. I have one quick clarification that goal 23 you talked about. So can I call that as a dimer, because I see it's a fused to one of the metals?
Goal 23.
So where you see this?
This one.
Yeah. So just this one. So here you see that your gold cluster is got fused. So can you call it a dimer, or in which you have some polymer as a trimer, tetramer? This is just a clarification. I do not know. Just wanted to know.
I think this structure is constructed by sharing 3 atoms.
So can you call it a dimer? That's my question.
Yeah, I think we can call it dimer. And the
dimer usually when you have a gold bond, we call it like AU2, AU3, a trimer, tetramer. But when many of the metal got fused, can we still call it as a dimer, trimer, tetramer?
Yeah, the hexahedral motif remain on both sides, so I think we can call this as a dimer. Okay. And I think that the bonding scheme between these 2 are different. 3 atoms are share, and the single atom is share. And this looks this may be corresponding to CC single bond, CC double bond, CC triple bond. So the bonding schemes are different, but both of them can be categorized as the dimer of the superatoms.
How about calling it as a fused dimer?
Fused dimer. Yeah, you can say fused dimer. This is also a part of fusion.
Yeah, I could see this is a gold vertex fused molecule. But in other case, you have a 3 like phase fused. I don't know. Just a quick clarification. I just wanted to educate myself whether it can do.
But this is my personal maybe explanation.
Yeah, nice chemistry, nice molecule. Thank you.
Sundar, inorganic chemists would like to probably refer to this as a fused dimer. I don't know. You will have to say whether for us.
No, I mean this is the one. That's what I'm telling you.
Will you accept that kind of a classification? Was Sundar that my comment was?
Okay. Thank you.
Thank you.
We have several pioneers in this field joining us. I see Professor Robert Wetton, Professor Jianping Jia, and we have Manfred Kappes and Horst Hahn. Well,
so here's a question from Thomas.
Yeah.
Yes. Hello. Thank you
Hello.
very much for a lovely talk. I was very happy to see it.
Thank you very
I have a
much.
question about the gold 11, and you mentioned, actually I have two questions, but one is about gold 11, and you mentioned the instability of the cluster unless you somehow stabilize it with an extra different ligand with carbene. Could you comment on, for me, on the instability of the gold 11 when stabilized, when covered only with phosphines and those chloride atoms? How does it decompose? Is it some sort of disproportionation where it goes to bulk gold and gold 1+? How does it behave in a solution?
Yeah, that's a very good question. And can you see the slide?
Yes, I do.
So the left one is the optical absorption spectra after heating. So you can see the red peaks gradually decreases, and the new peak appears at around 560 nanometer.
Oh, yes.
So this corresponds to the localized surface plasmon resonance. This means the particle size increases after decomposition, after heating. So maybe some of the ligands, phosphines or chlorides are removed, and then they fuse together to form a little bit larger clusters, larger particles. So this is the fate of the gold 11 and the heat treatment.
I see. Thank you.
And the single phosphine, this phosphine can be replaced with carbene. So this blocks this behavior. So I guess the initial step of the decomposition is the release of this phosphine, which is located between two chlorides. And if we block this, then the stability is enhanced like this.
Thank you. And my second question, if I can, still have a bit of time. My second question, can this instability of gold 11 be used, for example, when you deposit these clusters, when you want to deposit these clusters on some substrates such as alumina or some iron oxide? Can it be turned into an advantage, assuming that you have those little clusters well separated one from the other, to sort of deposit on the substrate these islands of 11 gold atoms and use this instability to sort of activate them on the surface of something, whatever it is, for catalytic reasons?
Yeah, that's a perfect question. Yes, actually, so we are using these atomically precise clusters as precursor to make a heterogeneous cluster system, a catalytic system. So we deposit ligand protected clusters on solid support, carbon metal oxide, and then in many cases, just heating. Heating induces the ligand desorption. And if the loading of the cluster is not so high, we can avoid the sintering induced by heating. So then ideally, we can create atomically precise naked clusters on solid materials by the process you suggested. But this is not so easy in many cases. But ideally, it works as a synthesis of atomically precise catalyst on solid.
Thank you very much. Thank you very much. It was a lovely talk.
Thank you very much.
Professor Tsukuda, can I ask a question?
Yes.
Thank you for your inspiring talk. So I'm very interested in your electron transfer between the two clusters. So what will be the driving force for this electron transfer? Like 2 minus and then the neutral charge the cluster.
Yes, it's also a very good question. Yeah, the answer is the difference in the electron affinity of the two systems. Actually, this process is exothermic.
Okay.
And, this exothermic comes from the electron affinity difference between 2 minus and 1 minus. And the 2 minus is very unhappy because of charging energy. It's very high in energy. So this is the driving force for this electron transfer reaction.
So how about the stability, like your 7 electron cluster compared to 6 electron or 8 electron cluster?
Stability, stability against what? Yeah, these clusters are formed as a stable species, nearly 100%. If we mix these two 1-to-1, we have a 1-to-1 7 electron system in a stable form.
Okay. Okay, it's very interesting.
Thank you.
Professor Wetton, you have a question. You have switched on your video, I see.
Yes, it's the sun is just about to rise here in California and Arizona, and I'm
good morning.
Thanks to Professor Tsukuda and Professor Pradeep. I'm alert now, awake at this hour, and no, seriously, I wanted just to make a comment and get some possible reactions. Beautiful talk, but I wanted to return maybe to the slide, this nice explanation you have of the superatom model and its predictions. If you could, please, Tatsuya. It's the one where you have your work extending over a very wide mass and size range. And then there it is, number 13. I believe it's 13, 13. Maybe not. Yeah, 13 will do. Slide number 13, yes. And I just want to remind everyone that the electron count calculated, for example, at the far right, 84, okay? 84 electrons at the far right. Now I see it, yeah, 84. That this has a hidden assumption. The assumption is neutrality of the cluster fully dressed with its ligands and staples and all that. It's the assumption of neutrality. And I think that I agree with you that that's a safe assumption for the clusters in their later life when they're being analyzed and, you know, after exposure to oxygen and light and so on. But I would caution that it's not very well established that in the reaction conditions that produce these clusters in high yield, that selectively produce these clusters, that they are neutral. So let me give a couple of counterexamples to that. In that case of the gold 144, which is labeled gold 114 for the core, we showed in some earlier theoretical modeling work that if one assumes a negative charge, -6 or -8, that quite a nice large gap opens up. And so we don't know experimentally for certain whether under the strongly reducing conditions that the clusters are normally synthesized, we're not that confident that that such strongly negative, highly reduced forms are not the dominant form. The voltammetry on the final products, shows that it's quite easy, facile to change the charge state over a wide range. Of course, when they're highly negative, they're very reactive. They're very good electron donors, so one doesn't expect them. If I may just have one more minute, I'd like to point out an extreme recent example. We could talk about old examples from Dahl, Larry Dahl's lab in Wisconsin, where they were getting 4- and so on for their crystallized products of different clusters. But a very recent example came to our attention in the meeting in Galveston Island. I know some of us were there, Professor Pradeep and Professor Tsukuda, maybe others, I don't recall, just 2 years ago. And this is a cluster that's used unwittingly, unknowingly, used in the very popular synthesis of gold nanorods, which are not clusters, but gigantic nanostructures, but very popular, very much applied. And this group in Rice University, there in Houston, they isolated, they identified a gold 32 cluster, which is kind of a magic number for geometrical reasons too. But this gold 32 cluster has 20 bromine ligands, and it has a charge of 12 minus. And you may ask, how is it possible to have 12 minus, or to know that it's 12 minus? And that's because it's identified with 12 counter cations, quaternary ammonium cations, the CTAP, popular, detergent thing. And it was a bit of heroic effort to identify this. They call it the seed, the missing seed cluster that forms the nanorods. How could they do this? Because the moment this is exposed to an oxidizing environment, it becomes it's a strong electron donor, like I said. But anyway, I hold up that example. They characterized it by the MALDI, mass spectrometry. It looks very good. And it's a reminder that under the strongly reducing conditions under which we all like to form, to generate our selected clusters, that the charge state can be quite different, quite a bit more negative than the products that we finally, as we finally store them and characterize them. So thank you for your patient.
I see. Thank you. So under reducing environment, maybe we can get multiply charged and negatively charged clusters which satisfy the electron count closure.
Yeah. Yeah. Thank you.
Thank you. Thank you for your suggestion.
That's a correct summary of what I was trying to say, that one can achieve those closure. I just have a lot of faith in nature to be very selective and to produce structures which are not only geometrically magic, but also electronically have the satisfy both, so-called doubly magic with respect to electrons and atoms. And so I'm resistant to this this proof, which is on this slide. That's all.
Okay. Yeah. Thank you very much.
Yeah.
Great. Nature, well, give it enough time, nature will show the magic, huh? All the magic that it can show. Well, colleagues, are there other questions? Well, it has been a wonderful evening. Thank you, Professor Tsukuda, for that nice lecture. Various aspects of the science that you very ably articulated. They point to new directions, and many of those directions arose a lot of attention from the audience. I'm sure that more work is needed on several of those questions of electron transfer or proton transfer or dynamics or structure stability or stability on surfaces or stability of large clusters or intermediate that are there. All of these are fascinating. So I wish you all the very best in your future endeavors and continuing endeavors. And we look forward to greater interactions in the course of time. Thank you all. Thank you. For joining. Please join us next month for the third edition of this lecture series. Thank you. Good night.
Thank you very much.